Croeso! GCSE maths can take you interesting places. Let's look at one. A lot of the maths you study at GCSE is quite old and was discovered a long time ago, and you might reasonably wonder if there are even any questions still left to answer. What are maths researchers even doing all day if we already know the value of pi and how to solve a quadratic? But there are loads of questions that mathematicians don't know the answers to. They're called open problems, and they range from very simple questions that I can explain to you in a couple of minutes, through to mind-bending fundamental questions about mathematics that mathematicians can spend lifetimes working on. One nice example of this is a problem called the perfect cuboid problem. We're surrounded by cuboids of all different kinds, and we have a lot of mathematical tools to help us answer questions about them. For example, if this cuboid is 85mm wide and 720mm tall, how could we calculate the length of this diagonal on the front of the cuboid? And how can we calculate the diagonals on each of the faces? If the sides of a general cuboid measure A, B and C, can you write down expressions for the diagonals D, E and F? Pause the video now if you want some time to think about it. We actually only need one familiar piece of maths to calculate that diagonal, Pythagoras' theorem. Each of the three diagonals uses a different pair of lengths, and we can work out the length of the diagonal on each face by squaring the two sides of that face, adding them together and taking the square root. For this cuboid, it turns out we get a nice satisfying result. All of the edges of the cuboid are a whole number of millimetres, and all the diagonals are a whole number of millimetres as well. And in general, this might not necessarily be true. For most cuboids, you'll find that at least one of the diagonals is not a whole number and has a whole bunch of grotty decimal places after it. So what are these special cuboids? We call them Euler bricks, after the Swiss mathematician Euler, and they have a particular combination of side lengths that are whole numbers, and their diagonals, which we calculate using Pythagoras, are also whole numbers. But can we find an even more special cuboid? Well, maybe, yes. There's another diagonal in here, the diagonal inside the cuboid between an opposite pair of corners. If you want another puzzle to work out how we'd calculate the length of the 3D diagonal of the cuboid with sides A, B and C, pause the video now. In order to calculate this length, we can use Pythagoras again, taking the height of the cuboid and the diagonal of the base, which form two sides of a right-angled triangle, with this 3D diagonal called the space diagonal as its hypotenuse. So, can we find a cuboid that has whole numbers on each of the edges, whole number diagonals on each of the faces, and a whole number for this 3D diagonal through the middle as well? If someone did find one, it would be called a perfect cuboid. And it turns out that this is an open problem. We don't actually know if one exists. Nobody has managed to find an example of a perfect cuboid, nor has anyone managed to prove that such a thing can't exist. Another nice example of an open problem concerns another triangle, Pascal's triangle, which is created by adding together two numbers to get the one between them in the row below. It has infinitely many ones down the outside edges. But there's only one 2 in this triangle, here in the top row. I'm talking about the number 2 on its own, not the digit 2. And there are only 2 3s, and 2 4s, 2 5s, and 3 6s. And a question you might reasonably ask is, how often do numbers occur in this triangle? Which numbers occur most often, and how many times do they appear? And again, this is a question we're not sure of the answer to. There's a conjecture dating back to the 1970s called Singmaster's conjecture, which says that we think there's a maximum, and it's maybe about 10, but no one has managed to find anything that occurs more than 8 times. 3003 is the current winner, which occurs twice here, twice again in row 78, and twice again in the row that starts 1 3003 and ends 3003 1. But that's it. Nothing has been found that occurs 9 or more times, but there's also not been a proof that 8 is the limit, or if a limit even exists. These kinds of little problems seem fairly abstract, and it's not even necessarily clear why they're important or worth solving, I guess apart from the satisfaction of a puzzle solved and learning a little bit more about the universe and how it works. But there are some problems in maths that are very, very important and may take years, decades, or even lifetimes to solve and connect to hugely important pieces of maths. In the year 1900, the mathematician David Hilbert nominated a set of 23 open problems in maths that he thought would be the big challenges of the century. Some of them were solved, others were shown to be unsolvable, and others remained out of reach. Then, in the year 2000, the Clay Institute, an organisation in America, picked out 7 problems that they called the Millennium Prize problems. And these were all big questions from areas of maths. Solving them would be key to unlocking whole new fields of mathematics. Some of the problems were to do with modelling physical systems, like the equations behind fluid flow. Others related to computation and how complicated calculations are if you break them down into steps a computer can perform. One of the Millennium problems was also a Hilbert problem. The Riemann hypothesis, which connects prime numbers and complex functions, was still unproven and continues to be even now. Of the 7 Millennium Prize problems, one has been solved. The Poincare Conjecture, which is to do with 4-dimensional shapes, was proved in 2004 by a Russian mathematician. And in fact, these open problems, the simple ones and the complicated ones, won't stay unsolved forever. And if they do get solved, they'll be by someone who enjoys a puzzle and isn't prepared to give up until they've got the answer. And using the tools you're learning now, maybe we can chip away at these open problems and learn a little bit more about how the universe works. So if GCSE can get you here, where can A-level maths take you? I'll leave you to find out. Hoil!